All right, Peter, take it away.
All right, folks, welcome back to C++ 20 in Chromium. This is part 3 of a 4-part series. We've already had talks on the spaceship operator and orderings, and then on templates last time with concepts and constraints. This talk is going to be a little less single purpose. This is a little bit of the grab bag of other cool stuff you can do. And then our final talk next week will largely be about stuff you can't do or stuff that you could help us do. So in this talk, we have basically 3 sections: some new Constness keywords, in case you already weren't confused by const versus Constexpr, and some new algorithm and container functionality, and then finally some useful utilities and sugar. So let's jump into the new Constness keywords, constinit and consteval. So both of these I'm going to explain by first taking you back to Constexpr and clarifying, like, what does Constexpr do, and then using that to explain the new keywords. So Constexpr variables. So what is a Constexpr variable? Semantically, like, we think of this as basically a compile time constant. In fact, it's kind of sort of like just saying const something, which is part of why the distinction is not clear to a lot of people. But specifically, Constexpr variables do 3 things. The first thing is they ensure that the variable does static initialization. So if you don't know much about initialization in C++, it's extremely complicated. But one of the things that is true is there's static versus dynamic initialization. Static initialization here means that the value of the variable is initialized by the compiler before the program starts. It's basically stored in the executable. Dynamic initialization, on the other hand, happens sometime while the program is running. Oftentimes, variables are initialized during like an initial startup phase that happens before you even get into main. There's like something that will go and initialize like global variables, and this is part of why we have all these prescriptions in the style guide about what you can do with global and namespace scope variables of complicated types. But static init means there's no runtime costs, there's no concerns about init ordering versus other items, and I think I'm going to talk a little bit more about that. The next thing it does is it makes the object actually const qualified, which means while it's alive, you can't change it. In fact, a compiler might even put it in a special section of the binary that's designed to be used for read-only data. So you don't initialize it when it starts, you don't change it while it's alive, and then finally it does constant destruction, which means that effectively the compiler can just tear it down for you without having to run complicated code at runtime. So it can do a few things, but they can only be Constexpr themselves. You can't like deallocate from the heap. You can't do other things that are going to dynamically change a bunch of stuff in program state. So static init, const while it's alive, and then constant destruction. That's what Constexpr is. If you remember those 3 things, then we can explain constinit very easily. So let's talk more about the static init phase of construction. This is a phase that's historically caused a lot of subtle bugs. This is known as the static initialization order fiasco. If you've encountered that phrase before, which I think is a very descriptive and nice phrase for it, I always like using the word fiasco, then you'll probably be familiar with this. But here we have some sample code where in 2 different files, we've put 2 different variables, and we've made the initialization of one depend on the other. And as humans, this dependency is kind of obvious, and we know what we want this code to do. We want A to be 1, and then B to be A, which is 1. So both B and A should be 1. The actual thing that happens is, we don't know. It's indeterminate. The standard doesn't say whether A is going to get initialized first or B is going to get initialized first. And of course, if B gets initialized first and the compiler runs code that copies the value of A, but A doesn't have a value yet, who knows what you get in B? So what actually happens likely is going to depend on the actual order that you passed these object files to the linker, because it's probably going to just like take them in order or backwards order. Who knows? Now, this is solved if you have A and B as Constexpr, because they're doing static init, so they can't depend on each other at runtime, and therefore the compiler is going to catch you if you try to do something like this, and it's going to say, like, for one, when they're in different source files, b.cc isn't even going to compile anymore, because it's going to say, I don't know what the value of A is. So then when you put A in the same file and you make them both Constexpr, then the compiler says, oh, okay, now I understand how these work. Either you put them in the right order or you reverse them and I will complain at you. So making things Constexpr makes them break at compile time if they're wrong. And that's great until you actually need that behavior, but you don't want A and B to be Constexpr because you can't use one of those other things about Constexpr. Like, for example, if A and B, you don't want them to be constant during their lifetimes, for example. In this case, you use constinit. Constinit does the first part of Constexpr. It does the static initialization thing and nothing else. This object is not constant during its lifetime, and it might do complicated things in its destruction. We don't know. We don't care. So this is basically a strict subset of Constexpr. It has no effect on the generated code here, likely, because even without writing constinit, the compiler might have been able to optimize the initialization of myobj, but constinit makes sure it happens. It breaks your compile if it doesn't happen, which is a very useful thing when you want to guarantee this into the future. And there is actually one nice thing that this does, which is if this is a thread local, it tells other users of the thread local, hey, this is already initialized. You don't need to worry about checking like a guard variable to make sure that it's been initialized correctly or not. That's sort of a minor detail, but this is part of why our style guide says you have to use constinit on thread locals, just in case you ever run into that and wonder what that's all about. So the semantic of this isn't so much this is a constant, it's just this is initialized by program start. How do you use it? Well, put it on the declaration and the definition. Technically, you can get away with doing it less. Don't get away with doing it less. Just put it everywhere you declare or define this variable. The one problem with this is it doesn't address destruction order fiascos, which can also happen. Like if you tear down one variable and then while you're tearing down another variable, that other one refers back to the value of the first one. That's basically the same problem as the static init fiasco, but at destruction time, we do have those in Chrome. Yay! And the only way I know of to get rid of this right now is that we turn on a warning. There's a client warning called exit time destructors. We even have a config for it in our GN files, but sadly it is not on everywhere. So it would be turn that on and fix that. So just in case any of you are looking for some code base cleanup to do, that would be one. The other downside, of course, is that this has like more verbiage, like, hey, I needed to learn yet another const thing. But thankfully, you will run into constinit much less than Constexpr. Okay, and then the other new const keyword, consteval. All right, we're going to explain this one from Constexpr also, but this time instead of talking about Constexpr variables, we'll talk about Constexpr functions. So what is a Constexpr function? Well, a Constexpr function is a function that you're allowed to call at runtime, just like a normal function, but you're also allowed to execute it at compile time if the compiler wants to. Now, clearly, if you want to do that, the arguments to it have to all be constant expressions. Otherwise, there's no way the compiler can do it at compile time. So here at the bottom, I'm showing an example where we call this Constexpr function called divide ints, and the second argument is a constant expression because it's just the number 2, but the first argument is x, which is some runtime determined variable. The compiler doesn't know what that is, so it can't execute the code for divide ints. It might be able to inline the code, but it certainly can't execute the code at compile time. So this one is always called at runtime, and that's not a problem. A Constexpr function can still be called at runtime. That's okay. If the arguments are all constant expressions, and the result is used in a constant expression, then it has to be evaluated at compile time, because otherwise the compiler can't initialize that constant expression that uses it. So this first line I have here, where we call x equals divide ints 2, 3, that has to be done at compile time because we're stuffing the result into a constant expression. Otherwise, we couldn't init x, which has to be initialized at compile time because of the Constexpr on it. So this will be done at compile time. And then the second line, we're trying to use it in a constant expression, so it will be executed at compile time, and it will cause an error at compile time because we're dividing by 0. The implementation of divide ints does a division by its second arg, and we pass 0, and so like instead of being undefined behavior or whatever divide by 0 like does, I don't even know if it's UB or like what it is. This will deterministically like error at compile time. This is part of the motivation for doing more things at compile time, is that they eliminate undefined behavior and turn it into like a well-formed, no, your compiler whines at you. The third line, however, is not using this in a constant expression. It's passing constant args, so it could be evaluated at compile time, but it doesn't have to be. And the standard says, in this case, the compiler gets to do what it wants. The compiler can evaluate it at compile time, in which case you'll get a compile error. Or it could evaluate it at runtime, in which case you'll compile just fine, and then at runtime you'll crash with divide by 0. This is probably sadness, because we probably want to be a little bit more deterministic than this if we really wanted this to happen. So consteval is kind of like a subset of a Constexpr function. You'll notice subtly I changed divide ints to now be consteval instead of Constexpr. Consteval means it has to be evaluated at compile time. In fact, it doesn't even emit code into the binary. It's only used by the compiler. So now divide ints, the first thing works fine, just like before, 2 divided by 3. And the second thing crashes, well, not crashes, errors at compile time, just like before, 2 divided by 0. The third thing also won't compile now because we force it to be done at compile time, 2 divided by 0, and the compiler complains at us, which is probably better. So if you have a function that you know you want to use only at compile time, like say you're doing some mathematical calculation or some initialization of a big array that you have like a helper function to compute all the values in the array, strip the prefixes off compile time strings or other processing like that, you can make it consteval and know that it's not going to go into the binary, so it's not going to bloat your code, and we're going to catch any errors like when we compile, which is a great thing. Okay, that's the 2 new const keywords. Oh, why is the assert gone? The assert. Oh, yes. Yes. Okay, so here in the Constexpr version of divide ints, I asserted that b doesn't equal 0 so that we would have basically a runtime check. I guess I could have written this as check instead of cert, since we're assuming the context is Chromium and not just general C++. But because we don't have b available at compile time, we don't know. Now with consteval, we don't really need to do that, because if we know the value of b at compile time, so we know for sure that if b is 0, we're going to divide by 0 and get a compile time error. You could just as well like leave some kind of precondition in there. And in fact, I think the way that check works is when the check fails, it invokes like a function that is not Constexpr, And therefore, like, you would probably crash at compile time because it says like, oh, the compile is not allowed to do this, not allowed to invoke a non-constexpr function from a consteval function. Could the compiler just return not a number? I don't believe so. This is one I would have to actually like test on Godbolt to make sure I understand what happens. I'm pretty sure passing 0 to this at consteval time is actually a compile time error and not well defined as returning not a number. And in fact, I don't even know if it would be not a number or if it would be like inf or like, I'd have to test this, but I'm pretty sure I tested this when I wrote this slide and that it was a compile time error. Fingers crossed. Okay. So, algorithm stuff. In C++20, we get a cool new bunch of functionality called std ranges. So in C++11, we already had these various things in the algorithms header, but they were a pain to use. Because if you're looking at this code, like, this is ugly and hard to read. We've got all of these different params, and we're like passing things multiple times. It's convenient here that I'm working on containers with short names like URLs and tokens, but if I had like long names, like this would really suck because now you already have to have a tip to call like .begin and .end or something. So this transform and this find call are legal, but like really ugly. In fact, often uglier, longer, harder to read than just writing a raw loop, which is why so many people on exposure to these said thanks but no thanks and continued writing raw loops. In Chromium, as of the last several years, we've had a backport of parts of std ranges that we call base ranges. And as you can see from the top thing, these are much nicer to use. They're much shorter, they're much more readable, they're actually more powerful because they have something called projections on them, which lets you sort of like inline do a transform of the input before you do the operation on it. I'm using that in the find call here, where that third argument, that address of token ID, that's saying, hey, take your input, which is a container of tokens, project it through the member ID, which means convert each token to its ID. Then find the desired ID on the projected values. At first glance, this probably sounds like kind of convoluted and confusing, but this is actually a lot easier once you get used to it than using lambdas just to like unwrap parts of your input. So this is super nice. In C++20, we now have the official standard library version of this, which you'll note looks very, very similar. In fact, in this case, it's precisely identical, except for base has been changed to std. It's not always identical. There were a few differences in terms of like return types. And in particular, one of the things that's changed in the standard library version is that the standard library version does extensive constraint checking. If you remember my previous talk on concepts and constraints, all of these are templated functions that have very long lists of constraints expressed as requires clauses that they require the input to match, and therefore ranges is actually much more aggressive than the old standard library algorithms about yelling at you when you try to do subtly wrong things. It can catch certain kinds of like dangling pointers and use after free bugs at compile time just because of the preconditions, for example. So thankfully, you don't need to know the differences between base and the standard library version because this porting has already been done for you. I already converted all of the base ranges stuff over to std and removed base ranges. It's gone. We already use the std ranges form. So you can and should, and in fact, if you try to use ranges, must use the bottom form today. Tom says, theoretically, without, say, back inserter, this form of transform should be unsafe buffer usage. Yeah, I'm not sure exactly what that would look like without back inserter. Like if you're saying if you had already resized specs to contain enough slots for the number of things, and then you were just using a normal iterator to like write over the elements of it. That you're right, that would definitely be unsafe buffer usage. If people aren't familiar with unsafe buffer usage, I will touch on this a little more in talk 4, where I'm going to talk about spans. So if you are excited about spans, or if you don't know what a span is, you should definitely watch the talk next week. So these algorithms are cool, and now that they're more powerful and more easy to use than the old C++11 versions, I'm going to give my brief tour through the algorithms library. I did something like this in my C++201 talks a few years ago, but probably a lot of people haven't seen those or don't remember. So just in case you are still writing raw loops for a lot of things, raw loops are fine. They work perfectly well. They're easy for the compiler to optimize in most cases. But often they tell the code how to do what you want instead of actually directly saying in English what you wanted to do. And I find in terms of readability and correctness, it often is better if you're in the habit of saying what you wanted to do instead of how you wanted to achieve it. So being more high level and using the ranges forms, even when they don't provide benefits in other ways, I find superior. So here are some of the things that already exist in case you weren't familiar. We have algorithms, and this is not an exhaustive list. We have algorithms that check like characteristics or predicates over a group. Like you can test, hey, is there anything in this container that matches this? Instead of having to do like find or some manual like loop through and test each element and then, oh, I found it, great. You just say like, hey, any of these this way? Similarly, I just mentioned find. Find is kind of the workhorse of all of the algorithms. And its sibling find if, which takes a predicate instead of an element. There's also search, which is the same sort of thing, except you need to find a whole subsequence of elements instead of just one. There's lower bound and upper bound. These are extremely useful if you have like a sorted range over some condition, and then you need to find the points in the range where the condition like starts or stops applying. So for example, in the Omnibox, when we have ranking of the items in the dropdown, where we're saying like, hey, where is the ranking like, you know, greater than 1,000, or, you know, when is my confidence less than such and such? That's what lower bound and upper bound are for, and equal range, which does both. We have algorithms to copy and transform elements. So if you're moving things from one place to another, you can reach for these. Transform is actually probably the thing I use the most personally in my own code. Basically does a copy with adjustment along the way. There is range algorithms that reorder elements. Rotate is one of the most underused range algorithms. It basically takes one or more things in your range and moves them to some other place, shifting the other elements around. So like you can take a group of things and shift them up to the front of the container or shift them to the back of the container. Moving them in the middle, you can do too. It's just less common. There's also partition, which is pretty useful. Splits a range into two pieces based on whether the elements fit a predicate. Do that a lot in certain parts of the code base. No computer science related talk would be complete without mentioning sorting. So there is a generic sort algorithm, which is highly optimized for lots of different general purpose cases. I think I just saw something go by the other day that said something like, for integers, make sure sort uses radix sort, which is, you know, or linear time instead of n log n. But there's stable sort, partial sort. There's something to check whether a container is sorted. Obviously, you could do better than this in certain cases when you have like particular knowledge of your input, but these are good general purpose things to use. We've got set operations in case you have containers that are working like sets of elements and you want to compute like what's the intersection, what's the union of both of these things. You can do those sorts of operations with algorithms. We have some of this stuff as harder to use facilities elsewhere in base, but the ranges algorithms are a good thing now. you can quickly find like the minimum or maximum elements or values in a whole range. And it's just gives you an idea of like what kinds of things are in the algorithms libraries. So now that you don't have to pass .begin and .end, these are really easy to call, and with projections, they're very powerful. So I definitely recommend that you look into using these if you don't already. And then a few other things that are kind of algorithm-like, but aren't technically in ranges. There's a new contains member function on some containers. So the old way to do this is slightly cryptic and inconsistent. If you're looking for like, hey, does my something contain a something, then it depends on what sort of a something you were looking in. If it was a string, you have to use like string find and compare to endpos. If it's a map, you use find and compare it to .end. And then if it's a vector, there is no member find and you have to use an algorithm. So 3 different ways of writing the same thing, which is a bit awkward. In Chromium, we added a facility called base contains, which not only says what it does on the tin, but also is like shorter and harder to get wrong. So this is very convenient. C++20 now adds this as member functions on some types, like string and map. You'll notice the 3rd line for vec, I still wrote as base contains. That's because there is no vec contains. Now, coming in C++23, which I say on the next slide, we get ranges contains. So we at least have a ranges form of contains for vec, but vec is still not going to get a member contains. So if you don't like that, like, hey, I'm using member functions on one and I'm a free function on the other, that I dislike this inconsistency, I want to do it the same everywhere, then you can do the bottom thing I have on this slide and use base contains everywhere, and it still works. We don't plan to get rid of that. So that's a perfectly reasonable alternative. But I happen to like reaching for member functions when they're available. I think stir.contains is slightly easier to understand than base contains stir comma substir. So that's cool. We also have erase and erase if. So those of you who have been erasing things from containers for some time are probably familiar with what I'm showing here, which is called the erase remove idiom. But if you haven't actually erased things from containers in C++ before, you might not have encountered this weirdness. There's a convenient standard library algorithm called remove, and when you call it, it doesn't remove anything. Yay. It turns out remove basically just shifts the non-removed elements to be in the front of the container, and then what's left at the end of the container is unspecified. Might be the removed elements, might be garbage, who knows. And to actually get rid of that end portion of the container, you have to call a second function, erase, and say, hey, erase the range from between where my remove call returned, which is like the end of the real elements, all the way to vec.end. This is kind of awful and can go wrong in multiple ways. So this is audience participation time. Quiz question: how many different ways can I screw this up? Or maybe I should phrase it as, like, name me like a way that I could get this wrong as a coder. There's an obvious and some less obvious stuff. Forgetting the erase, yes. Ellie says forgetting the erase in chat. Totally easy to do this. There's nothing that the compiler will do to stop you from just calling remove and then leaving that there and leaving garbage at the end of your container. It is a foot gun. Tom writes the very subtle passing an iterator to a different container. Like if you pass, remove from vec.begin, vec.end, and then you pass something other than vec.end, you pass like vec2.end. That would be an exciting thing to do that would totally break stuff. Julian knows that remove is a terrible name. It is a terrible name, but sadly it's what we have. There is yet another way of getting this wrong no one has mentioned yet. Give you a few seconds to try to think of it. This is subtle. So this one has bitten me before. Julian says wrong iterator. I'm going to assume that's similar to Tom's suggestion of passing the wrong thing. Iterate over vec after remove. Yeah, like, well, if you try to access the elements at the end, I mean, it's well defined to do that, but who knows what you're going to get when you look in them. So the subtle answer here is yes. What Robert is saying for getting the second arg to the erase call. Vec.erase has a single arg form and a two arg form. If you pass just one arg, it means erase the element here. If you pass two args, it means erase the range from one to the other. Wow, what a footgun that is. Because if you call erase like std remove blah and you don't pass end after that, it will happily remove just the first of the like dead elements at the end and leave all of the others. And once again, compile just fine. Nothing will complain at you. Horrible, like, foot guns abound way to hold this. So now that I have like thoroughly motivated why this is evil and you should never call erase remove, which we do several hundred times the last time I checked in Chrome, take a look at the much better ways of doing this in Chrome. Before C++20, we added base erase and base erasif. And these do like erase a value or erase all the things that match this predicate. These are just so much safer. It's not just that it's shorter and more readable. It's that it's safer because you're not going to footgun yourself with this. And then C++20 now gives these to us in the standard library. You can erase on a vec, or you can erase if with like a predicate. Weirdly, you cannot pass a map. There's like specific overloads for erase, and it supports like vectors and certain other containers, but like you can't erase like a key from a map, but there is a member like map.erase with a key, and there is an erase if for map and pred. And I'm so confused by this state of affairs. I don't understand why the API is the way it is. And I only mention this in case you ever run into it and then are like, what the heck is this compile error? It's the standard library being weird. But other than that odd asymmetry, there are erase functions now. You should absolutely use this pretty much every time you would ever think of reaching for the remove algorithm. There's a migration bug to go to these. I would love to see somebody tackle this and get to the point where we have no calls to remove and a pre-submit against ever using it again, because it's that dangerous. String prefixes and suffixes. Starts with and ends with. So this is yet another one where it's like way more footgunny than you thought it was. If I'm writing starts with, and by the way, for the pedantic among you, I apologize that the little 1, 2, and 3 comments here are not quite horizontally aligned. It's not my fault. It's a monospace font, and it turns out the characters in the monospace font are not all the same width. So just thanks a lot, font designers, for cursing me. Anyway, starts with, so if you're looking for whether a string starts with something, you can write it at least these 3 different ways. Maybe there's more, I don't know. Number 1 is actually efficient to use string.compare, but it's kind of error prone. Like nobody really reaches for compare, so it's like hard to remember that the result is one of these ints like strcomp, and so you have to like test the negation of what you thought you were testing in order to get the right answer. So easy to do it the wrong way. Number 2 is inefficient. If you try to take the substring at the beginning and then check for equality, it's unnecessarily going to copy a bunch of characters, the length of your substring. Number 3 is actually even worse, and I find a lot of instances of this in Chrome. The complexity of this is unspecified, and in fact, it may be as bad as string length times substring length. So just like don't write it in these ways. When you're saying like, wait, but how am I supposed to write it yet? Hold on, next slide, I'll get to it. Ends is actually even more exciting. I tried to write it the same way as the best of the options on begins, which as you can already see is like really long and ugly and horrible, and it's still buggy. The code on the screen here has a bug. What is the bug in this code? Can you spot it? Yes, Robert has it correct. So this is not checking that the substring isn't longer than the string. And in that case, we're going to underflow. We take string length and substring length. These are both unsigned. We subtract wraps underneath 0. That's well defined. It's going to loop around to be a very, very, very large number. And this is going to basically probably like read way off into the middle of nowhere. So the security people will be angry at you. This is a really easy mistake to make, despite the fact that I already wrote a whole ton of verbiage. Now I have to write even more. So in Chromium, we already had base starts with and base ends with to do this much more readably. Now we get them in the standard library. Now you'll notice this is like raw byte match comparisons. This is not the sort of smart like, hey, my strings represent actual human language. You know, they might be Unicode. So there's whole like, you know, code points that might be, you know, longer than 1 byte, et cetera. Like we're not doing any of that stuff. We're doing like raw byte comparisons. If you have to do fancy things like case insensitive comparison, which really should probably be like normalized instead, and a bunch of other stuff, you should be reaching for our I18N libraries and ICU. But this is suitable for like, no, I have like raw bytes and I need to compare them. Do they start with X or do they end with X? You can do this now. String dot starts with blah. Says what it does. Easy to use, very efficient, and totally safe. Migration bug is available if you want it. Okay. Thus ends the whirlwind tour of new algorithm things in the standard library. You'll note that many of these algorithm things are things that we had in base already. We kind of have a policy of trying to provide like backports of useful C++ utilities. But this is part of why in the talk that I gave recently on What's Up with Base with Sharon Yang, thanks Sharon, I said something like base is like the one weird place in Chrome where it's actually worth your time to go through and see what's in there because there's so much useful stuff. Like you could be getting the benefits of things like these before we get to C++ 29 or whatever. Actually, that doesn't exist yet. But Julian says, for the simple use case, it doesn't matter what the encoding in the string is, right? Yes, if you know that you're just checking like byte equality, then it doesn't matter what the bytes actually mean. You, of course, have to be careful. Oh, thanks, Sharon. Go/what's up with base. Is apparently a convenient Go link just to go to that talk because you want to see me give more talks, right? And in this case, you get the added bonus of Sharon being there also. So not just me, in case you don't want to see just me give more talks. So the simple use case doesn't matter what the encoding is. Asterisk, yes. There's probably cases where you search for some set of bytes that is like the subset or the subsequence, the prefix of a longer valid set of bytes or something. I don't know. I mean, not in like UTF-8 because anything that's in the middle of a character is going to be marked that way. But anyway, the upshot is like we use strings in a lot of places in our code base for things that either we know are ASCII, where encoding is like clear, or you have the same encoding on both sides, or it's not even a human readable string at all. It's actually bag of bytes that we're passing around as did string. For all of those cases, this is appropriate. Useful utilities and sugar. This is like a collection of miscellaneous utilities. And it's hard to tie together a collection of miscellaneous utilities into a single coherent story instead of just having a bunch of slides that are like, hey, this, this other thing. And then you're like, your eyes glaze over and you fall asleep at your desk. So I have invented this stupid function. This function is very poorly motivated, but contains many of the things that we could improve with new stuff in C++20. So we have a templated function here that takes like some kind of a t, and then it takes an operation to do, and it switches on that op and says, like, what am I doing? Am I like rounding up, rounding down, rotating, what am I doing? And then does that. And I spent absurdly too long trying to come up with plausibly correct implementations of these different algorithms that still fit on one line in a slide. So, yay. But we have this function to do some bit ops on an input. How could we make this better using new facilities in C++20? Well, the very first thing, and probably for this code, the biggest bang for the buck, is a new header called bit. This has low-level bit operations. Now, maybe you don't run into these in your daily life, but if you work in the network stack, you definitely run into these in your daily life. And certain places in Blink and certain parts of like math code and base and rendering and various other things, you often need to do bit-level stuff. And when you do, you should reach for this header because it has kind of all of the common things that you would want to do, like swap endianness and rotate things and count leading zeros and round up to the next power of 2 and all of that kind of thing. We had a header for this called basebits.h already. The functions were not exactly parallel to the bit header. They had different names and different functionalities. But one nice thing about the bit header, all of these functions are Constexpr. So if you provide them compile time constants, the compiler will have the option to optimize them. And they're very efficient even at runtime. They generally all use intrinsics to map down to like raw assembly instructions to do things at the CPU level. So you can be assured that you don't need to go like crack open some like hacker black book of low-level bit algorithms to do stuff fast. You can just use these. And then if we use these in our contrived example function, not only do we get rid of a lot of confusing implementation details, but the result probably runs faster and it's almost certainly less buggy because I definitely did not check my handwritten implementations before to see that they were correct for edge cases. So this is just, big win if you're actually doing bit ops. Yay! And then tangent war story time. So this header is actually the reason why Chrome is on C++20 today and not C++17. Because back in April of 2022, I wanted to explore, hey, if we could use C++20 modules, which are another thing that's coming up in talk number 4, what kind of build time wins could we get? And unfortunately, Clang and GCC didn't support modules at that time. Luckily, MSVC supported modules already. So I was like, well, if we could just build parts of Chrome with MSVC, I could experiment with this. Well, I thought, okay, I'll try building base with MSVC. How hard could that be? Like we used to build with MSVC years ago. It can't be that hard, can it? Narrator voice, it was hard. So it turns out like the big blocker to that was when we were doing a bunch of bit level operations and our implementations in base were not Constexpr and we needed them in a Constexpr context. And the only way to do them fast at runtime was intrinsics in MSVC, but the intrinsics weren't marked Constexpr. And there was no way to like switch implementations between compile and runtime, yada, yada, yada. Like the upshot was I said like, wow, we could actually like do this if only we had, like the bit header and we actually just ported Chromium to C++20. Like Clang supports the rest of C++20, okay. So let's just port all of Chrome to C++20, then we'll have the bit header, then we can use that here, then we can build base in MSVC, then we can experiment with modules, and then we can know what the compile time win would be. How hard could that be? And so it took about, I don't know, 18 months or something. Thankfully, most of that was not engineering time. Most of that was just waiting time. It was a couple of months of engineering time to actually do the C++20 port. But after doing that, then we got to C++20. And since then, I have not actually gotten back to doing any of the rest of the steps on that yak shave. So I still don't know what MSVC's module support would give us. And in the meantime, we've gotten better module support from Clang. So if we wanted to experiment, we'd probably go that route now. So like, yeah, I don't know if the moral of this story is like, it was all for nothing, or if the moral is like, I don't know what the upshot is, but that was how we got to where we are today, is we did this. Okay, off a bit. The next little convenient bit of sugar that we have, params of type auto. You may be familiar with this already in lambdas. So if you write lambdas, you've probably written a param of type auto in your lambda. Now in C++20, you can do it on your function. Your function can just be written as taking an auto or a const auto ref or a whatever. And the form on the bottom will generate code that is exactly equivalent to the form on the top. It basically just declares an implicit template parameter and says, oh, you have this template type. If you have multiple autos, they each get their own unnamed template type. So they'll deduce separately. So when we use this in our function, now, thankfully, we have saved one line at the top because we've not written template, blah, 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 blah. We've just written auto, do bit op, and it takes an auto T. And this will deduce the right return type because I've been consistent in the switch, so I don't actually need to use a trailing return type here. Also, we have using enum declarations. So everybody loves enum class, right? Yay! I don't know. I mean, enum class is kind of cool because it like scopes names and they're no longer implicitly convertible to integers, which is usually a thing that you don't want to implicitly do. But it kind of sucks because now you have to qualify the names everywhere. And if your enum has a really long name, you write long name, long name, long name over and over and over again. And it's really annoying. Well, behold the power of using enum. Now we can do like using enum long name, and it pulls the like elements in the enum into scope there. So it basically works the same way that like a using declaration would work for just about anything else. Now, on giving this, one of my test audiences was like, wait a minute, you can do a using declaration in the middle of a function? And I'm like, yeah, you totally can do that. You can do a lot of things inside functions, like write other functions inside functions and like do really nifty stuff. So can the using be within the switch block? Probably, I don't know. Try it on Godbolt. Not sure. I did it above the switch block here. So much like a using namespace, we use this in our fancy thing. We have now made all the cases easier to read because instead of saying bit operation type : on all of them, they have gotten shorter. This is more compelling when you have like a several hundred line long switch statement, but hey. And then designated initializers. And I apologize because this one isn't going to map back to anything in our contrived example because shoving designated initializers also into that same function and still fitting it on one screen was just like a step too far. I couldn't figure out how to do that. But we already allowed designated initializers several years ago as an extension, even though they were technically C++20. But now C++20 is here and they are formally part of the language. Designated initializers require your type to be an aggregate. What the heck is an aggregate? Basically, an aggregate is a bag of data. It's a type that doesn't have user-defined constructors on it. So you can see here, foo just declares some data. It doesn't have constructors. Now, in Chromium, this fights hard against the Chromium style plugin that's constantly telling you that you need to add constructors and make them out of line. And that also makes things not aggregates, which means you can no longer use designated initializers. And this has been a long-running battle internally where a bunch of us yell at the maintainer of that, poor Daniel Cheng, on Slack, and then he's like, yeah, I'll fix it at some point, and then he has better work to do. But hopefully sometime this week, he told me this yesterday, sometime this week he plans to make the plugin less aggressive so you can use more aggregates. I don't know what that means. I will believe it when I see it. But when you can use designated initializers like this, it means that you can name what your different variables are getting initialized to instead of just having a bunch of values that who knows what they map to. And that's clearly more readable. It's also usually less error prone. So this is super cool. Now, I do actually have a few other slides of miscellany, like really fine-grained stuff that's new. And if there are no questions, like we totally would go on to those. But given that it's getting late and this is the most important stuff, we're going to do a wrap-up here and just see like where things go. So the takeaways from the main portion of this talk: constinit. This is for your initialized at compile time non-const variables. And in Chromium, you'll most likely see that on thread locals. But there's probably a few other cases for it. Consteval, compile time only functions. And then there's new versions in the standard library of a lot of stuff in base. If you did not know about the stuff in base already, that's cool. There's way too much stuff in Chromium to know, but definitely like become aware that base has cool things. And there's lots of migration bugs available to go use these more. Like just because we make them available doesn't mean we automatically have passes that go back and magically transform the code base to use them. So certainly like code cleanup opportunities abound. And the final bullet I put here, keep learning new techniques. Like there's a continual trickle, whether it's in the standard library or it's in base or it's in Absol or whatever. People are constantly adding like new ways to do fundamental things that make code safer, shorter, better, faster, etc. There should never be a stop to when you're learning. I mean, that's probably a general statement about life, but like even within Chromium and C++, like there's always more stuff that you could learn and that could make your code better and code in the project better. So like definitely keep like looking around and learning new techniques. That's going to continue in the future. So I will stop there for the moment. For all of you who tune into my talks just to see what memes I reference occasionally on slides, I'm sorry I didn't put any memes in this talk because I'm not very funny. So I apologize for that. But questions? Ellie.
We have a few minutes left, and you alluded to this, so I think it's fair game for me asking this. What is the deal with modules?
I'm totally going to say, hey, watch next week's talk. Because I will talk about modules in next week's talk. Just to plug next week's talk now, next week's talk is the last talk of the series, and it's going to cover span, it's going to cover coroutines, modules, more stuff in ranges. So if you're a language nerd and you have read the standard and you're like, wait a minute, there's all kinds of things in C++20 you haven't touched on. What about these? Well, that's where they all fall. And if you are not a language nerd and you didn't know about any of those things and are like, should I even care? I will attempt to motivate the talk into why you should at least care a little bit. Like asks, are there plans to remove stuff from base that are now C++20 features? For example, base erase versus std erase, where the standard library versions fully can replace them? Yes. And by plans, I mean there's probably a bug on file that says we should do this someday, and no one is assigned to that bug. And no one will ever do that bug unless a motivated person steps up and does the bug. But yes, like we totally could replace base erase with std erase, I think. Probably won't replace base contains, because as I point out, like there's cases where there is no like good replacement right now. Are those bugs in the code health list? Generally, things like that are not in the code health list, because when we nominate things like that for the code health rotation, they get kicked back as specific to base, so base owners should take care of it, which is like, lol, do you know what we do with our actual time? We work on our real jobs and not maintaining base. And also low net value, because it's just cleanup, so it's not actually fixing a security bug or something, so we don't care. Sadly, this sort of maintenance gets left to individuals and not the code health rotation. Other questions? Okay, if there are none, feel free to interrupt me, but I will speed run the few slides of my appendix, more miscellany, just to say what some other trivial stuff is. There's a numbers header. You get common constants like pi and e. Woo! I should have worn my shirt from last week. My last week's talk had pi and I talking to each other, but it would fit this slide. But I didn't know if I'd get to this slide. That's clearly why I didn't wear it. You also have templated versions for non-doubles, so migration bug for that. Let's see. There's a version header. If you are a web developer, you are likely familiar with the concept of like feature testing for individual feature support on your, instead of just looking and saying like, hey, am I on like Internet Explorer 6 or above, you know, or something like that. You test for like, can I use the such and such feature? The version header is now here. Ellie asks, how old is under has include? This is well defined as of, I believe, C++ 17. So has include predated the version header, which comes in C++ 20, and the version header gives you like fine-grained testing for tons and tons of things. There's hundreds of different macros in here that you can test, and you can not only see what features exist, but what version they're at. We have assume aligned, which tells the compiler, hey, like, you know this pointer? Well, here's a version of that pointer that you can assume is hard aligned to this value, and therefore vectorize it, you know, using this cool technique on your CPU or something like that. This is, of course, a nice foot gun if it's not actually aligned to that value, because the compiler doesn't know, so it's like, okay, and then you will blow up. But what's with a little more UB in the language? So we have that. We have lerp. Lerp is linear interpolate, and in this case also extrapolate. So it interpolates or extrapolates a value between or outside of start to end based on a t, and then it handles all these weird edge cases, because like, well, what if you passed like infinity, you know, and like all kinds of different things, you know, what if your equation ends up being crazy? It can do all that stuff. For that reason, it generates much more code than actually just hand rolling it yourself. But in most places where we're doing this, we don't really care. Like in UI code, the difference between an interpolation on an animation where each once every like 16 millisecond step takes like 10 instructions instead of 2 instructions, don't care. So like, I would just use lerp. Similarly, std midpoint, find the midpoint between two values. That's kind of cool. So we have that. Let's see, std s size for when you wanted the signed size of a container. And the return type is not s size t, because that's POSIX. That's not C++. C++ does not have s size t. POSIX does. Just in case you had ever used that in your talk. This is not very useful to us, because using spans and ranges really mitigates the need to ever refer to something like s size in your code. And then there's like a whole list of even more stuff that's so low level that I'm just going to be like, no, talk about it elsewhere. And you can go read our C++ features.md doc for this. So that's the speed run through my miscellany. And with that, we are over time. So thanks all very much, and we'll wrap things up next week with part 4. So hope to see you all then.